let's work on these other example problems. And in this video, we're going to focus on part B, C, D, E, and F. Now, did you try them? Did you take a stab at these, at least, to see if you're going to get the correct answer or not? Folks, that's the only way that you can learn organic. When I tell you to stop the videos, do try to answer these questions. See if you can predict these products, and then play the next video and double check your answers. Only with that process can you figure out why you made the decisions that you did and why they were incorrect decisions. And then you can adjust for that, you can modify for that in the upcoming example problems and the upcoming questions. So let's take a look at B. Honestly, none of these were really any more difficult than part A, but we're still going to work through them one by one. The more examples I can give you, I think the better off you're going to be. So here we have a reagent, and they have told me that this reagent is going to undergo elimination. You're adding sulfuric acid and heat. That's elimination, folks. All right. So what does elimination do? Well, I start off with the reagent structure, and off goes the OH. There we go. And then we need a neighboring carbon to donate a hydrogen. And either one of these are fair game, but which one's the better choice if there is a difference? And there is a difference. The better choice here is going to be the neighbor that points below. Why? Why did I choose this position instead of this one up here? Well, the answer here is, again, delocalization. Double, single, double cause you trouble. It will always happen if you don't watch out for it. So because this is a delocalized system of network now, these electrons can now move throughout this part of the molecule. It helps increase the stability of that molecule. So that way, folks, this molecule is a much happier molecule, and a happy molecule is a stable molecule. So if I did it up here at the top, those two double bonds are too far away. That would be a double, single, single, double. And that is not delocalization. So double, single, double cause you trouble. That is delocalization. All right, so there is the preferred major product for part B. Now, let's take a look at C. All right, so for C, they give me CH3, CH2, CH, and off of this is an OH, and then a carbon that has 3 methyl groups, one on top, one to the side, and one down below. So yet again, I'm looking at delocalization here. All right, so with the delocalization, that means this alcohol group needs to be eliminated. This alcohol group, there it goes, off it goes. And we form this carbocation in the middle, right? Well, this carbocation is going to allow maybe for some rearrangement to take place. I mean, this was a secondary carbon, a secondary alcohol. So rearrangement can happen. This is an E1 mechanism. Well, if it goes to the left, it's secondary, it's no better. Why move? If it goes to the right-hand side, this has the potential of being a tertiary carbon. So it knows that. It's going to shift because of that. And we need to do a switcheroo. So this carbocation and one of these methyl groups will have to switch. And the reason it's a methyl group is because normally it would be a hydrogen. 1,2 hydride shifts, they happen first. But this carbon had no hydrogens. It only had methyls to move, and a methyl is okay as well. So a 1,2 methyl shift happens. Now this moves our carbocation, so now at this carbon, I look up, and I look to the left, and I look to the right. And I try to figure out which would be the better buddy to take the money from. Which is going to give me a more stable double bond? Well, if I go right-handed or up, both of these are methyl groups, it's the same stuff. So these two, again, are twins. If the double bond happens between those two carbons, folks, that gives me 2 hydrogens on that sp2 carbon. And we have another option that lowers the number of hydrogens down. It's more inward. Anytime we can go more inward, that's always going to be a better scenario for us. So does the left-handed carbon have a hydrogen that it can get rid of? Sometimes they don't, but this one does. So an elimination reaction can happen. It's going to take this hydrogen, whoop, there it goes, and we form a double bond between those two carbons. So there's the elimination product using sulfuric acid and a little bit of heat. If you look at this sp2 carbon here, I have two groups on it. They're both different. If you look at the sp2 carbon on the right-hand side, it also has two groups on it, but this case, they're the same. Whenever we have a same group like this, we really cannot give you a cis-trans or an E or Z notation. So we just kind of leave it off. There you go. You could make the argument that, well, you know, we can try to show it, but folks, quite honestly, you're wasting your time. So we'll leave it at this and call it a day. D. CH3, CH2, 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 and then OH. All right, 1, 2, 3, 4, 5. That is a pentanol. It's one pentanol. This is a primary alcohol here. And a primary alcohol is going to have to undergo elimination. Now, we've already talked about the weird things that happen with primary alcohols. So with the primary alcohols, they kind of happen like normal in the beginning. So the the sulfuric acid will go in and dehydrate this molecule. So the OH group is going to be targeted. Whoop, there it goes. And then a neighboring hydrogen is also going to have to be removed. And there's only one possibility here. That's it. And that's this one. Whoop. And we have two bonds that go in between those two carbons now, not just one. Okay, so this is kind of a middle stage. We know that when we do these primaries, they are very susceptible to attack. They're very reactive. And folks, I just generated water in the system, and water is going to immediately attack that double bond. And then here we go back to the alkene reaction. When I go back to the alkene reactions, this is acid and water gets attacked onto a double bond, and what we see is a break of the double bond, and two sites of attachment open up here and here. Well, hydrogen plays with other hydrogens, so that goes there. That's called the Markovnikov addition. And then we have an OH that goes into that inner carbon because of that. It's a more stable carbocation. Well, the elimination is still going to happen. We still have sulfuric. We still have heat. So an elimination is going to happen again. And folks, this is why the double bond shifts inward on the inside of the alkanes. So this OH group, whoop, there it goes. And this carbon's going to look to the neighbor to the left, and whoop, there it goes. And a double bond forms between those two. That is more internal. It's not as susceptible to attack. It's harder for things to get in there and react with. So folks, there you go. Now this one, we can give you a little bit of insight to stereochemistry, and this is how we would do it. So if you give me this as a correct answer, or as an answer, I would count it correct, because I did not specify stereochemistry. But if I did want stereochemistry, I would say that in the question, and you would have to clearly show which one of these would be more stable. So these two carbons in a double bond, they're there. And this carbon to the left has a hydrogen, and it also has an ethyl group, so CH2CH3. Over here on the right-hand side, that carbon also has a hydrogen and a methyl group. Now, I know that things that are trans are going to be more stable. That's just the way that it is. And I'm saying trans in this case because we can compare hydrogens between each other. Cis and trans is used for hydrogens E and Z when you can't really compare hydrogens across the board. So we see this zigzaggity that goes on. The hydrogens are on opposite sides. That also forces the alkyl groups to be on opposite sides, which increases the stability of the double bond or the alkene. So folks, here's the answer for part D if I need to show stereochemistry. And sometimes they don't ask for it at all. If I wanted to name this structure up here without the stereochemistry, well, this is a 1, 2, 3, 4, 5 longest carbon chain. So this is a pentene because of a double bond, and this is going to happen at carbon number 2. So 2-pentene would be that product. If I want to be more specific, though, this is still a 2-pentene. It's still 5 carbons in total, so pentene. It's still happening at carbon number 2. That's where the double bond is. I give it the lowest group number. But here, I can actually put the word trans in front of it to tell you a little bit about the stereochemistry of that molecule. All right, so there's D. Let's work ourselves up to E. I see a CH2, a double bond, a CH, a CH2, a CH2, and then an OH. Oh gosh. What are we going to do here? I mean, there's a double bond here already. Yeah, so what? I don't care. You shouldn't care either. I mean, this elimination has nothing to do with double bonds. What have we talked about all this time? We've said elimination in this route with sulfuric acid and heat targets the OH group and it rips the OH group off. That's all that we've said. So I don't care that there's other groups on there, and you should not either. You do this the same way, folks. There's no difference. So here, acid, heat, attack, gives it a black eye, and it eliminates it. Whoop! There it goes. Well, the neighboring carbon here is the one to the left. It's the only choice, and it has to take a hydrogen away from it too. These are buddies. They're looking out for each other. Bell money. Whoop! There it goes, and a double bond is formed. Now, this is a terminal alkyne, or alkene, right? A double bond on the end. So normally we would go through a second step and we would say, well, this is a terminal, it's very exposed, it's going to react, and then it shifts inward one more time. But not in this case. Why? Well, I think you know what the answer is. Double, single, double, cause you trouble. Delocalization. That's what goes on. So because this position has primed this molecule now for a delocalized network, double, single, double, this highly stabilizes the molecule and it will not go through that movement a second time. So we don't really have to worry about that second round, even though that this is a double bond that's on the end of a molecule, and that's the problem that primaries always give us. So, folks, there's your answer. Nothing more than that. Delocalized stabilizes the molecule. Now let's look at F. All right, so F gave us a ring. There we go. And off of this ring, we have a CH2 and an OH. All right, so this CH2OH, even though it's a ring, folks, the template's the same. You know what I'm going to say. You already know what kind of sound effects I'm going to make. I'm going to eliminate. It tells me in the directions, sulfuric acid, heat. So I'm going to target this OH group, and I'm going to whoop, there we go. And then I'm going to look at this carbon's neighbor. This carbon's neighbor is right there. And that carbon's neighbor, I hope, has a hydrogen because we need to take the hydrogen away in order for this elimination to go forward. If a hydrogen was not there, there's no other choices for that carbon, and an elimination is going to be very hard to do. But guess what? It does. It has one. If I look at this carbon, it's got one bond up, one bond to the left, one bond to the CH2 group, and that fourth bond is the hydrogen that is not drawn. So there is a hydrogen there, and that's good news because this elimination needs to whoop it off of the molecule. And when that happens, we get a double bond that forms between that carbon and the ring. Now, here's the issue. This is also regarded as a terminal alkene. It's at the end. And we have just generated some water just like before. So there's no difference here. There's no difference. That water and acid will attack the double bond again, and we see a rearrangement just like we did before. This is a primary alcohol. That's what we started with. So it doesn't matter if it's on a ring, that double bond is going to break. Two sides of attachment open up, here and here, and hydrogen goes on first. This is an alkene reaction. Again, that lecture module's open if you didn't quite get alkene reactions back in the day. So H and OH gets added onto the molecule. H comes in and plays with the other H's. There we go. Well, that forms a CH3 group. That gives me the more stable carbocation where the OH group will go at that point. And then elimination will happen one more time. This is its way of getting that double bond away from the end. That's the whole reason that this happens. And it happens with the primaries every single time. So elimination will happen all over. This elimination will target that OH group that was here, and guess what it does? Whoop! There it goes. And then it targets a neighbor. Which one? It doesn't matter. They're both twins. It's the same thing. The carbon that's up above is the same as the carbon that's down to the left. They're both a CH2 group. Nothing else on this ring that's going to help determine which one's going to be better over the other one. So I'm just going to whoop a hydrogen off of that one, and I form a double bond that I can draw straight up. If you wanted to do it to the one to the left, do it. If it makes you feel good, do it. It's a correct answer. There's no difference. So if I go back to this set of questions, let's sum up one thing that might have been lost. This OH group, that is on a tertiary carbon, and this shifted. So tertiary, folks, there you go. That eliminated. This one, this was a secondary alcohol. That one eliminated. Delocalization helped judge where. For part C, this one was a secondary alcohol. There was a shift. That shift took place to give it a tertiary position, but in the beginning it was secondary. For part D, this was a primary alcohol, and the primary alcohol took two steps. It formed the double bond, then broke it, then reformed it. That's the issue with primaries. For E, this one was also a primary alcohol. The difference, though, no two steps happened. Normally, it would have. But the reason that two steps did not happen here is that delocalization stopped it. So when this double bond formed, I ended up with a double single double, caused you trouble, and this is where I stopped. And then for F, this is yet again another primary that formed a double bond here at the end, and just like with normal primaries, it breaks, and then it reforms again closer to the inside. So those are the things that you have to watch out for when it comes to elimination. Now, let me take another step forward. Now that we've done those example problems, I'm going to give you yet again another option. Oh gosh, another option. Yeah, there's another option. You know, there's so many different ways to do these reactions. We like to give you options and kind of explain why there's so many different choices that are out there. So here's the thing. With the first option that we've talked about, this was H2SO4 and heat. Well, I don't know about you, but I feel very uncomfortable turning untrained people loose in a laboratory that's maybe never been in a lab before with concentrated sulfuric acid that can eat their skin and give them basically trips to the hospital if they're not careful. And in addition to that, heating that concentrated acid up extremely hot. Do I want hot acid spewing all over the place in a lab? The answer is no. So some people are really sensitive over that. You know, they're like, oh no, this is sulfuric acid and we're heating it and I've got to put on face shields and gloves and aprons before I can work with it. And I'm like, just go and get it and just work with it. Just be careful. I mean, if you can work with hot grease in your kitchen to dump French fries in, then you can work with this hot sulfuric acid. You just got to know how to handle it if it gets it on you. Well, because of that, there is another option. It doesn't use nasty acid and high heat. And it does the same thing. It pretty much does the same exact thing that acid and heat will do. And this second option is using something called a phosphorus oxy chloride. And this is going to be represented with a POCl3. Now, just like with the substitution grouping, you remember HBr added onto an alcohol, HCl added onto an alcohol, HI added onto an alcohol. Rearrangement could take place. The same thing happened here in this step, right? Rearrangement could take place. That was a traditional acid heat. Well, in the second grouping of our substitutions, we did things like PBr3, PCl3, SOCl2, tosyls, and all of those prevented the rearrangement. Well, look, think of this as PCl3 or PBr3. I have POCl3. There's no difference. So if that helps you keep everything straight, the phosphorus oxy chloride prevents rearrangement. That is one of the good things of using this mechanism, using this reagent with an alcohol. Maybe wherever that OH group is, that is where you want to eliminate. You don't want carbocation shifts to happen. Well, the acid and the heat is going to allow it. But the phosphorus oxy chloride not only is a little bit safer, but it also prevents the carbocation rearrangement from taking place. So, let's look at overall general scheme first. What you would see in these reactions is something like a CH3, CH2, CH, CH3 with an OH here maybe. And we're going to add POCl3, and this requires a solvent. What do you think that solvent's going to be? What have we used this whole time? You got it. Ding, 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 ding. This is pyridine, and pyridine is not only the only requirement, but it's also 0 degrees Celsius. Yeah, we're going to have to take place in a super cold temperature. You know, if you look at refrigerators, you're looking at like 4 degrees. 4 degrees C. That's a common refrigerator temperature. So this is going to have to stay cold in order for this reaction to go forward. So what does it do? I mean, what kind of reagent would we make? Folks, it's the same. There's no difference here. You use the same thought process. I'm going to redraw my reagent. So CH3, CH2, CH, CH3 with an OH group. And what goes on overall, before we talk about mechanism, is the POCl3 acts just like the H2SO4 does. It targets this OH and it goes whoop. There we go. That carbon does not rearrange. That's the difference. It's going to stay there. Notice I didn't even question it. Will it shift? Will a 1,2 hydride shift happen? Will a 1,2 methyl shift happen? No, I didn't even question it. That's the good thing with the phosphorus oxy chloride. So the OH group leaves, and we look at neighbors. Which one is going to be the better neighbor to kind of move in with and get bail money with? And the more inward it can go, the better off it's going to be. So inward we go, and we whoop off that H, and a double bond will form between those two carbons, and that gives me the major product. That gives me the most stable product that's there. So phosphorus oxy chloride and sulfuric acid, even though they're different reagents, kind of do the same thing, folks. There's no really big differences here. We eliminate the OH in each case. We eliminate a neighboring hydrogen in each case. We make sure that we choose the side that gives us the most stable double bond in each case. The difference is that route 2, the POCl3, will not allow rearrangement to take place. Now, let's take a look at the mechanism. I know you hate mechanisms. I hate mechanisms sometimes too. But this gives us kind of a chemical explanation of what's happening. So let's take a look at this. CH3, and then a CH, and then a CH3. Let's say that this is the alcohol that we're going to be using. Let's add on POCl3. Okay, well, what does that structure look like? So P is going to be in the center, and we have an O, and that O is a double bond. And then Cl3, look at this, folks. Phosphorus is another one of these that doesn't quite need octet. I told you, they lied to you. General chemistry lies. They do it all the time. Here is one of those cases. Well, this poor phosphorus is caught up in a 4-way relationship. Gosh, they probably live on a plantation somewhere, you know, marrying 4 different people at one time. And, you know, as long as nobody bothers it, maybe that's okay. If it works for them, that's all that matters. So if the oxygen's happy, and if the chlorines are happy, and the phosphorus is happy, then why should it matter to anybody else what goes on? Well, here, they're not quite happy. Phosphorus is the only maybe bread maker in the family. Phosphorus goes out and works all day long, and then comes home to the 4 wives or the 4 husbands. And all those husbands or wives want to do is take. The reason that I say that is because oxygen is electronegative. Chlorines are electronegative. And there's not just one chlorine, but there's 3 chlorines all at the same time that's pulling electrons away. Well, if that phosphorus is going to be pulled in 4 different directions, you better believe, folks, that that is going to be a partial positive atom. Spread itself too thin. Should have known it. But that's how phosphorus is. And this oxygen out here, it sees that phosphorus and it says, something must be going on over here. I mean, those 4 atoms want to be in a relationship with phosphorus, and they're okay with it? I mean, what's going on? Is there something that's happening here that I'm missing out on? I mean, I want to be a part of this club. So this oxygen gets kind of jealous, and it's negative. So I start my arrow here, and it points to the positive piece like it does all the time. So this curvy arrow mechanism, bing, goes straight to the phosphorus. And phosphorus at this point says, oh, no. I can only tolerate 4. I mean, 4's enough. I can't do a 5th. So this phosphorus looks at what it has at this point, and it sees 3 chlorines and an oxygen. And, you know, between that choice of O and Cl, phosphorus looks at that ugly chlorine and it says, you know, I got a new husband. I've got a new wife coming in. And they're prettier than you are. And I only have room for 4. So, you know, chlorine, it was great while it's lasted, but wink, off you go. And that chlorine, and it takes it away. So here we form an intermediate. That chlorine has been removed as a leaving group. We have this CH3, this CH, and the OH group. That's how I'm going to draw it, just the same as before. But on this oxygen, there's now a bond. And that bond is to that phosphorus. That's what it reached out and got. And that phosphorus has with it the double bond O still, as well as 2 chlorines. So I know that this is looking ugly, but folks, there you go. Now I'm going to redraw this hydrogen in a way. I'm just going to draw that on a stick, on a bond. There you go. So it's still there. Didn't do anything with it, but I'm priming it up for the next step of the mechanism. Now, this oxygen, just like before, you know what's going to happen here. The oxygen bit off more than it can chew. That's just the common thing that it does all the time, and this makes it a partial positive, or in this case, a full-blown positive charge. There's too many bonds here. The formal charge is a positive 1. So oxygen says, uh-oh, shouldn't have did it. So now oxygen has a problem. It's got to get rid of a bond, and it's got 3. 1 to a carbon, 1 to a phosphorus, 1 to a hydrogen. Which one do you think it's going to get rid of? It's going to get rid of the easiest one that will pack its bags and go. And that's poor old kick around hydrogen wherever it needs to go. Again, I always feel sorry for it. So do you remember that solvent that we needed? Yeah, that solvent was pyridine, wasn't it? So pyridine is still going to be there, still going to be in play. We have this nitrogen-containing group, and there's this ring system on it, and this pyridine has some free dots, and the free dots of that pyridine, that's a negative area, looks for things that are positive, or what can be donated easy, and that is that hydrogen. Oxygen needs to get rid of it. Hydrogen has to go somewhere. So that's the purpose of the pyridine. So the pyridine goes in, and it grabs the hydrogen, pop, off it goes. Hee-hee, away they go, happy little life. And then these electrons from the OH bond go in to the oxygen. And when that happens, we form another kind of middle step here. CH3, CH, CH3. And off of this now is just a full-blown O. No hydrogen involved anymore. It's gone. And that O is attached to a phosphorus. That's double bonded O with 2 chlorines out here. Well, I can write 2 chlorines like that. Or, folks, what I can do here is just combine them. Make it a little simpler for us. And just do Cl2. I'm just doing some cleanup work. That's it. So there's one pyridine. That one pyridine took the hydrogen, away it went. I still have chlorine that's out there swimming around in solution, but we've not yet talked about the elimination process yet. We're getting closer, but we haven't talked about it yet. So what's the next step? We said elimination does not happen. Well, the reason that elimination does not happen is that this is almost like an E2 mechanism. The next step is going to take place all at one time. Do you remember what we kept doing? We kept saying, look at the neighbor carbon. That neighbor carbon has to have a hydrogen that it can get rid of. All right, so what I'm going to do is that with this neighbor over here to the left, I'm going to draw a hydrogen that's kind of down. I'm just making it so that this process is a little bit cleaner looking. But that hydrogen has to go. We have to form a double bond. How do we do that? Well, pyridine's a solvent. which means that there's tons of it. And there's going to be some more pyridine in solution. So that nitrogen's got a free pair of electrons, and there we go, away we go. And another pyridine's going to zoom back into the molecule, and it's going to see that hydrogen now, not the one on the O, but this hydrogen. And it's going to go, yum, 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 I like that one. So another mechanism step takes place. But it all happens at once here. So the second pyridine will come in and rip the hydrogen off of that carbon. Then that carbon will take those extra electrons and say, I've got your bell money, buddy. So here it goes. There's the double bond formation. And this carbon says, thank goodness, I'm at the police station. I was here waiting with a cop, so now the cop can go. And those electrons go off with the OP double bond O Cl2 molecule, which is a very good leaving group. And this is how we get our CH2 double bond CH3 as a product. That is the elimination reaction. We knew an elimination reaction was going to happen. My POCl3, phosphorus oxy chloride, oxy for oxygen, chloride for chlorine, takes the double or takes the OH, whoop, off it goes. Takes the neighboring hydrogen, whoop, off it goes. And a double bond forms in between those two carbons without rearrangement taking place. All right, so I think I'm done with the POCl3. So we're not quite finished with elimination yet. So we're going to come back in the next video. We're going to wrap the elimination section up for the alcohols before we move on to the next area of the lecture on alcohols, ethers, epoxides, and sulfur-containing groups. And we've not even made it out of alcohols yet. What did we sign up for?